So we're going to study the behavior of the function dxy as a function of x, as x varies on a fixed arc vp vq. So this is my arc vp to vq, and x is going to be a point somewhere along the arc. Initially, I'm going to start with x being equal to vp, and then it will move towards vq. And y is some point, let's just assume it's outside of the edge under consideration. It could be one of the endpoints vp or vq. So let's assume initially y is in the vertex set, okay? So it's going to be some vertex, say vi, okay? And I can be p or I can be q, that's permitted. Now, when you look at this situation, the distance from x to y is determined by some path whose length is minimum, okay? Now, that path, there are two choices here. Either that path starts at x, goes to vp, and then goes along some path to vi, or it goes from x to vq first and then goes along some path from q to vq to vi. Okay? So I've got two possibilities here. Now, if my shortest path from x to vi goes by first visiting vp, that means I move here along the subarc. And then from here to here, from vp to vi, whatever path I'm moving alongside of, that has to be a shortest path connecting p to I, right? Otherwise, of course, that would be too long. All right, so the length of this path, whatever it is, it's the length between vp and vi. I'm going to abbreviate that to dpi. I don't want to write too many stuff on the board because they tell me to write large and I can't really write too large. The board is not too large. Okay. This one, if my shortest path is from x and then to vq and then from vq to vi, again, I have to be going along a shortest path between vq and vi, whose length I'm going to abbreviate to dqi. Okay? So a shortest path from x to a fixed vertex vi must necessarily visit first one of the end vertices vp or vq. If it visits vp, then it must follow the shortest path from VP to VI from that point on. And similar argument goes for the other endpoint. Okay, so what that means is the distance between x and VI, the fixed vertex, is going to be one of two quantities, whichever one is smaller. So it's the minimum of two quantities. The first one going from x to VP, then from VP to VI, which means I go along the subarc x to VP or VPX. So that's going to be lambda x times L PQ. Plus, from P, I move along a shortest path connecting VP to VI. So that's going to be dPi. That's my first shortest possible path if I first visit VP. The other one is, of course, lambda 1 minus lambda x times the length of the arc LPQ plus the distance from Q to I. Now, this expression may look complicated, but it's not. Everything here is known except this x, or anything that depends on x. This is just a constant. Likewise, that's a constant. L is a constant, etc. But lambda x, 1 minus lambda x, well, they, of course, vary as you move along the edge. All right, so what I'm going to do is I'm going to change this to a simpler looking expression. So we observe that when x moves from VP towards VQ along the edge VP, VQ, the length of VPX changes from what to what? Well, when x is VP, the length of that subarc is 0. And as it moves, it starts increasing, and finally it arrives at LPQ. Okay? It is just contained in that interval from 0 to LPQ. Similarly, the length of subarc x to VQ changes from 1 to how much? Sorry, from LPQ to 0. Initially, when x is VP, of course, the entire length is consumed, and then it starts decreasing and finally gets down to 0. So if I define alpha to be the length of the subarc VP to x, then we know that alpha changes from 0 to LPQ. So I can write down the following. I can define a function, say g, which is, of course, dependent on the edge under consideration. So let's make it GPQ as a function of alpha. Its value will be defined by distance between x and vi. And we know that it's going to be the minimum of two path lengths. One is, so I gave a new name to it. It's alpha. Okay. It's going to be alpha plus dpq. The other one will be lpq minus alpha plus dq. Sorry, it's not dpq, it's dpi. Change that, please. Alpha plus dpi. The other one, lpq minus alpha plus dqi. So all I did is I just gave a new name to lambda x lpq. I just called it alpha. It's just the length. I just purified it. Okay? And this one, of course, becomes lpq minus alpha with that. Let me call this number one expression. It's the distance XVI as alpha changes from 0 towards the length of the arc. So observe that alpha plus dpi is a linear function because dpi is just a constant. Alpha is just it's a linear function with what slope? With slope plus 1. Okay? Because we take as reference the starting point, Vp. As you move to the right, the slope is plus 1. And that, the second function, which is lpq minus alpha plus dqi, is also a linear function with slope minus 1. So I'm talking about the minimum of two linear functions, one with slope plus 1, the other one with slope minus 1. Hence, the function GPQ alpha is the piecewise, is the pointwise minimum of two linear functions. If we plot those functions, the first one is alpha plus dpi, so it begins at value dpi, and it starts moving with a rate of 1, and finally arrives at how much? lpq plus dpi. The slope is plus 1. The other one, it begins at this value and ends at what value? At dqi. It ends somewhere here, dqi. And the initial value is how much? It's going to be lpq plus dqi. Yeah, that's how much it is. And my g function is the pointwise minimum of these. So my g is this. along this segment. It's the smaller. And then it becomes this one. So this is GPQ. At least we have something to start with. We have a broken curve, a piecewise linear function. It's got two pieces at most. It could have only a single piece. And what else? When will it have a single piece? Well, if one of the minimums dominates the other one along the entire arc, then of course it will be only a single piece, which is either increasing or decreasing depending on which one dominates the other. Okay? All right. So, but if it has two pieces, then the slopes are like this. And because it's the pointwise minimum of two linear functions, what kind of a function is it? It's a concave function. It's like a house top. Okay? So, the function GPQ is a piecewise linear function, linear concave function with at most two pieces. That's probably the most important property you will see that initiates the network theory, network location theory. Now, this property was first observed by Hakimi Please memorize this name, because that's an important name for network location theory. The entire network location theory started back in 1964 with an initial paper by Hakimi. He's originally Iranian, but he lived in the United States. He passed away 2 years ago, unfortunately, at the age of 70-something. He was an electrical engineer by background. Nevertheless, he was very active in location theory as well as in other network theory. He published many papers, and he's been known to be the father of network location theory. Well, actually, there are other fathers, but nevertheless, he is the one who seems to be the most well-reputed. He posed two problems in his operations research paper in 1964. One problem was the absolute median problem that I mentioned before, the mini-sum problem. The other one is the absolute center problem. Again, it's the minimax version of the same problem. He posed these problems, and this was the first time that these problems were posed with continuum of arcs rather than as discrete set of points eligible for locations. Okay? Of course, these problems were existent before. In fact, for example, the center problem was initially posed back in 1863, I believe, by Jordan, he's a French mathematician, but it was only the node-restricted version of that. The node-restricted version is quite straightforward because you just enumerate over the vertices by evaluating the objective function at each vertex separately, and then you just choose the minimum. This is innovative because, of course, in a transportation network, you've got points along arcs, so why not consider such points? And then to be able to analyze these two problems, he had to come up with all these stuff except the embeddings. He did that intuitively. Okay? He worked with this length function rather than the embedding stuff I gave you. The embedding came later. I'm going to give you some references for being able to read these things over in your spare time. do read them. When you read these papers, they are difficult. So my job here is to make them easy for you to understand. Sometimes I make them also difficult because I go into formalities. Nevertheless, formalism is only needed to carry over to even more advanced steps, but intuition always goes with formalism. Okay, so I always draw some pictures for you. If you don't understand something, just ask. That really helps. Okay, so that's the important property. And from this point on, we are in a position to be able to actually analyze the minisum and the minimax location problems, not only for single facility case, but later for multi-facility cases as well. But again, let me go back to that. There are three possibilities for that function. One is the one you've already seen, the two-piece version. The second possibility, you may have the first minimum dominating the other one all the way. So the function looks like this, because the other one is dominated. Now, sometimes when you go through some papers and some books, you will see that the dotted line actually in all books, it doesn't look like it's touching. It can be anywhere, but it has to touch there. There's a reason for that. Okay? I'm going to explain that in a minute. The third possibility is the following. Like this. Okay? Now this value is dpq, this value is dq, sorry, not dpq, it's dpi. This one is dqi. And this one, this is dpi, this is dpi plus how much? lpq. And this one, it's dqi, and that one is dqi plus lpq. Now, why do you think this one has to really actually touch the other one? Yes?
Otherwise, the shortest path to the vertex Q, I mean, would that be the shortest path? Because
okay.
The arc length PQ plus dpi would be a shorter distance than the otherwise di.
Okay, I got you. True. You see, this value is at the same time, if you just think of the dotted line, it's dqi, right? That endpoint is dqi. Now, what's the definition of dqi? dqi, by definition, is the shortest path length from q to I, which means that it has to be less than or equal to that one. Because this one is the length of some path. What path is it? This is the length of the path that goes from Q to P first along the arc, and then from P to I. That's a path. Is it a shortest path? It could or could not be. Okay? May or may not be. So this is the length of some path which goes along the arc Q to P, and then from here it goes to VI, which gives you this length. So this is the length of that particular path. that particular path is not necessarily a shortest path, it's just any path. The shortest path length is necessarily less or equal to that. But by assumption, we assumed that the first minimum in the minimum operator dominates or always achieves the minimum. So this is also less or equal to the other one at that particular value. Sorry, Qi. So they are equal. It's a minor point, nevertheless. Just take a note of that. Okay? You won't see that in books in the literature because people really did not think about this that much. Okay.
DPI is the shortest path from.
Which one?
DQI is the shortest path from Q to I.
Yes.
And DPI is the shortest path from P to I. It should satisfy triangular inequality.
Yes, but triangle inequality admits equality. They are both shortest. Yes. Well, actually, this dqi, whatever length it is, I just draw it this way, but it could be this particular path actually. Okay?
In this case, in order to satisfy triangular inequality, DQI cannot be greater than
Right. Yes. Yes. Well, the triangle inequality actually comes from the same arguments, you know. If you remember, we said this is just a side note which has nothing to do with what we're doing right now. But the third property for the distance was dxy less than or equal to x to u plus distance from u to y. And Hatice is saying the following. If you have x and y, and if this is a shortest path whose length is x to y, fine. There's some shortest path that gives you that length. Now, if you pick some point u here, which could be also on the path, nevertheless, for generality, let's just put it here. If you go first to u, then you go a distance of x to u. And then you go a distance of u to y. If you look at the union of this and that path, the lower two paths, that's just a path connecting x to y, which is not necessarily shortest. For that reason, the triangle inequality holds. If your u happens to be on the path whose value is dxy, then of course equality will hold. Sometimes, of course, equality may also hold if this is just another shortest path. Okay? So these are all possibilities. And your argument is actually correct. You can use the triangle inequality. Okay. I'm not going to analyze this situation where y is not a vertex. So I just assumed it was a vertex because the problems we deal with essentially always has the distance function from a given point, say from a facility at x to a vertex location. Vertex locations are the demand points. For that reason, I'm not going to go into that. And you can certainly do it yourself. No problem with that. It may require a little bit more thinking, especially if y is on the same edge. Okay, in that case, things become a little bit different. Yes?
Does y or vary?
Pardon?
In the second case, does y vary, or it is?
No, again, it's a fixed point, but it could be a non-vertex point. It's really easy. So again, if you have VP, VQ, if x is here, y is somewhere here, the same arguments will go. Nevertheless, if y is in some other edge, say vi, vj, and some of these vertices may coincide, no problem with that. Then of course, when you go from here to here, you have to visit one of the end vertices. So either you go this way and then here, or go that way and then here. These are shortest paths, or vertex to vertex shortest paths. Same way here. You may have two different shortest paths, one to this endpoint, one to the other endpoint. So the distance between x and y is this arc length, or this sub-arc length, plus one of these, plus the appropriate sub-arc length. Okay? So it's going to be the minimum of 4. But I don't have to go into this. As long as my y is outside of this edge, I don't care. There's a shortest path from VP to y here. I don't care how it goes. It's just a constant, because y is a fixed point. And there's another one, VQ to y. So that when you draw the picture here, it will again be the minimum of two functions. One is going to begin at distance VP y, which is just a constant because y is fixed, p is fixed. And then it starts going up like that. It ends with VPY plus LPQ. The other one is similar. It begins at VQY, and then in the other endpoint, it's LPQ plus that. Okay?
I think this is like decomposing the arc into two.
Exactly. If you want to be too precise, you can do that, but you don't have to. You can go along this as long as you know what this stands for. It stands for a shortest path length. So this actually here will be the shorter of either that or this. You see? Who cares? Well, if you have to care for other reasons, then of course you know what to do in that case. Okay? But if x and y, well, y is a fixed point here. When x starts moving along the edge, of course, first it gets closer to y, and then starts moving away from y. So the distance is a little bit different in that case. That I'm not going to go into, but you can certainly analyze that on your own. Okay? Okay, so let me go into the absolute medium and center problems now. First, the absolute medium problem. So let's first look at the absolute medium problem. Define the function f by f of x equals summation, the appropriate weight for the ith vertex. I assume wi are given. And let's just assume they are positive for the time being. You may assume they are non-negative as well, but let's just assume everybody is a demand right now. Times distance from a facility at x to vertex vi. And I sum this over all vertices. All right, so the absolute medium problem is to minimize f of x over all points in the network. That's the absolute medium problem. That's a combinatorial statement of the problem. Well, it's a continuous function, so it may not look like a combinatorial statement. Nevertheless, it's just it has nothing to do with integer programming or anything like that. Okay, it's just a regular optimization problem with f defined on n and mapping that into the reals. Okay, so for every point x in the network, I have a value function f, and I'm looking for the minimum of it. Again, does the minimum exist? You bet, because d is a continuous function as a function of x for each fixed vi. The positive multiplier here will still make it continuous. If you have 0 weights, you can just drop those terms from the summation, but I didn't want to bother doing that. And then, so each term, wi times dxvi, is a continuous function. The sum of continuous functions is continuous. When you have so f is a continuous function on the entire network, and because the network is compact, it has it admits a minimizing point from Alper Yıldırım's course. I hope. Okay. All right, so this is the problem. So the next question is, well, the existence is guaranteed, but how do you find it? That's the question. All right, so how do you find it? Before that, let me also define the function for the center problem. Let me see what notation I used. I guess I did not define so let's just define it to be f prime for the time being. Later on I may drop prime, okay? This time it's the maximum distance maximum weighted distance from x to every vertex, the maximum taken over all vertex indices. And your absolute center problem is to minimize the function f prime of x in the network. Okay? Again, the maximum of continuous functions is continuous, so again the minimum exists. At least one minimum exists. Your job is to find it. But first concentrate on the absolute median problem. So, we're minimizing the function f of x defined before, where x is any point in the network. Now, the first thing you will notice is that n is the union of finitely many arcs. So I can carry out my minimization for f along each arc separately, one at a time, and the minimum of arc minima will be the best for the entire thing. So this problem decomposes into arc problems. So I can take each arc, such as the arc whose endpoints are Vp and Vq, minimize the function f along that arc, and whatever minimum I get, I just put it on the side as a possible solution. Then I repeat the same thing for another arc, so on and so forth. You just do this for every arc, one at a time. At the end, you have as many possible candidates as you have arcs. Of course, certain arcs may produce actually more than one minimum, in which case you may also keep them on the side. And finally, out of all those finitely many minima, you just pick the best one. Okay? That's the idea. So let's just look at the arc-restricted problem. Minimize the function f in the arc Vp, Vq. That's my arc-restricted problem. Now I'm going to draw a picture for you again, which makes life very easy. This is my arc Vp, Vq. Now, this f of x is defined by the sum of wi dx vi. I going from 1 to n. I'm going to take these one at a time. In other words, take the first index I equals 1. When you look at that, without the weight, dx vi is either a two-piece linear function, concave, or it's a single-piece linear function. For generality, let's just pick it to be this way. This is just an example. And since I'm multiplying this function with a positive weight, the slope will change from plus or minus 1 to plus or minus wi. Does everybody follow that? Okay. Yeah. So, this is the function wi d vi as a function of x as x moves from one endpoint towards the other one. The only thing that changes is the slope information, but not the other. Çok gürültü geliyor değil mi arkadaşlar? Şunu bir söyleseniz biraz azaltsalar. Okay. Çocuklar çok gürültü yapıyorsunuz. Ders rahatsız oluruz. Okay, so this is only one of them for the ith one. When you change I, of course, the shape of the function will be different. So another one will look like, for example, something like this, say. Well, I did not draw it too well. Another one might look like this, etc. Some of them may be single piece. Let me also do this black, since the camera does not see red, I think. Okay, so when you have such a situation, what do we do? To form the entire function, we add them up. For fixed x, you add up at that particular x. So when you add them up, you just pick the appropriate values, add them up. When you add up all these functions, what do you think they will look like? You're adding, it will be piecewise linear. Also, the sum of concave functions is concave, so it will be concave. You said? How many breakpoints?
Yes.
At most?
2 times number of
2 times or 1 time?
powers.
2 to n? Okay, well, I'm waiting.
As many as arcs.
So let's just write it down. F is piecewise linear on VP, VQ. It is also concave because the sum of concave functions is concave. By the way, a positive number times a concave function is always concave, okay? The weights do not change the concavity property. All right, so if you allowed negative weights, things would be different, so please be careful with that. All right, so it is also concave since the sum of concave functions is concave. It has at most so many pieces. John says 2 to n, but I don't think so. How much?
Order n squared.
Something proportionate to n squared, Haluk says. What do you think? Is that right or wrong? It depends, but what's the worst that can happen? What's the most it could be? I have only 1 minute left, so I need an answer. N, yes. NS says it should be at most n. Well, this is true because when you add up these things, normally in this particular example, up to this point, the first breakpoint, you are adding up linear functions. So things will be linear up to that point, whatever it looks like. It may look like something like this. At this point, one of the linear functions under consideration changes. So up to this breakpoint, things are again linear, but one of them changed slope. So it will go something like this. At this point, it will change again. And there's another breakpoint here, which is really close by. So it will go something like this, and then something like that. Right? So in this example, each two-piece linear function can introduce at most 1 breakpoint. Each two-piece linear function has exactly 1 breakpoint, in which case the total number of breakpoints of the f function is bounded above by the number of breakpoints that can be introduced by these functions, which is going to be at most n. So this is correct. Yes?
I think I misunderstood the question. I thought the intersection points of individual
Oh.
concave functions.
You're thinking of the center problem, probably. Yes. Okay. So it's a concave piecewise linear function with at most n pieces. It has at most n pieces. Now, well, the pieces I count are the interior not pieces, but sorry, at most n breakpoints, which gives you at most n plus 1 pieces. Okay. Now, when you have a concave function on a closed set like this, where does the minimum occur? At one of the endpoints, right? A concave continuous function on a compact, a concave continuous function f on a compact set Vp, Vq attains a minimum at one of the endpoints or one of the extreme points.
Is this the basis for node optimality?
Yes. One of the extreme points. In our case, they are end vertices. So, of course, the shape of the function tells you what the entire story is. We're not done yet. We're not done. We have some kind of a piecewise linear function, which is concave, and you're looking for the minimum of this function. It's going to be either at this endpoint or at that endpoint. This is true of concave functions in general. Concave functions are functions of this sort, so it always holds. This is a well-known theorem. Okay? So, the minimum of one of the end vertices, the minimum either at Vp or Vq, gives you the minimum of the entire of the function over the entire edge, which means that the edge-restricted, arc-restricted problem is solved by one of the end vertices. There's a node that does the job. Okay? So the entire network problem is also solved by one of the nodes. That's a good result, because instead of having an infinite search, you can now restrict your search to only node locations. That we're going to take again next time. Okay?
What's the complexity of trying all nodes?
Uh,
Are we going to do that also?
You need to evaluate the summation per vertex, assuming x is a particular vertex. That summation has n terms. So assuming that you know the vertex-to-vertex distances, it would take the addition of n numbers, that's O(n) per vertex. If you repeat this for each vertex, it's going to be O(n) squared for the entire. But if you don't know vertex-to-vertex distances, then computing just the distance matrix a priori would also take O(n) cubed.